Hi, my name is Benjamin Dowling, and I am a postdoc at ETH Zurich. And this is Many a Mickle Makes a Muckle, a framework for provably quantum secure hybrid key exchange. This was joint work with Torben Hansen, an applied scientist at Amazon Web Services, and Kenneth Paterson, who runs the applied crypto group at ETH Zurich. So let's begin. So these scare quotes are meant to express is that in recent years, a lot of work has been done to create cryptographic tools that can withstand attacks by large-scale practical quantum computers. And indeed, as the existence of a conference like PQCrypto is testament to, one of the ways that we have this is post-quantum cryptography. But there are other tools that we can use to achieve this goal. And one of them is one that many in our community may be critical of, quantum key distribution. Now, as I'm sure we're all aware, quantum key distribution is a two-party protocol where parties exchange photons and basis information in a classical way and derive shared secret keys as a result. Now, this protocol is perfectly secure, unconditionally secure, according to the laws of mechanics, as physicists will happily tell us. So if that's the case and QKD is this panacea, well then why is NIST putting so much effort into the PQCrypto standardization process? And as again, I'm sure we're all aware, well, there exist problems with QKD. The first one is fairly straightforward. Deployment is expensive and it's quite difficult. And as a result of quantum decoherence, there exist limits on the distance between two communicating channels, two communicating parties. And those distances aren't huge. They're not practical. Indeed, it also requires an authenticated channel to exist between the two parties that can be used to exchange this basis information. And as a result, you could see quantum key distribution less as key distribution and more like key expansion. And attacks on hardware mean that even these guarantees of unconditional security can be undermined. So if we don't have this, perfect panacea, what is it that we as cryptographers can do? Well, it's fairly straightforward. Let's add more post-quantum crypto. So the motivation for this work came out of a project to create a quantum-safe encryption protocol. We wanted to create specifically a key exchange protocol that hedged against problems in deploying QKD by inclusion of post-quantum cryptography and indeed classical cryptography in order to establish a series of quantum-safe keys. The goal was to be able to run the QKD and these key exchanges as fast as possible in order to establish a series of keys in order to get very, very tight windows of security. So for what follows, our focus is going to be establishing keys for this communication channel. And that brings us to Muckle. So the phrase, many a mickle makes a muckle, is a North English phrase, I'm told, and essentially means from many a small thing comes a big thing. And that happily describes our approach, which is that we wanted to create a quantum safe key exchange protocol by combining quantum key distribution, post-quantum key chems, and classical chems to create Muckle, a quantum-safe key exchange. And since Muckle is a key exchange protocol, we had various security properties that we wished to achieve. The first ones are fairly straightforward. Key indistinguishability is the notion of security introduced by Bellari and Rogaway for assessing the security of key exchange protocols, and essentially captures the notion that the adversary is unable to distinguish a real from a random session key. From the same distribution specifically. And we wanted to make sure that we had key indistinguishability against quantum-equipped attackers. Similarly, authentication captures the notion that two parties executing this key exchange protocol together agree upon some sort of session identifier, which in our case, in Muckle, will be the transcript of messages exchanged between the two parties. But in addition to having normal or standard notions of security for key exchange protocols, we also wanted Muckle to have more modern notions of key exchange protocols. Being a hybrid protocol, we wanted to have breakdown resilience. And we also wanted Muckle to be robust in the face of various compromise paradigms. So we wanted Muckle to achieve forward secrecy and post-compromise security. So let's delve in a little bit more into what we mean here. So breakdown resilience was a notion that was introduced by Brendel, Fishman, and Gunther in 2019. And it captures the notion of a security of a hybrid key exchange protocol, even against failures in the underlying cryptographic components. In particular, in Muckle, what we're interested in is failure of the QKD and the post-quantum chem components. The idea is that even if the QKD fails, maybe due to problems within the hardware, we still get security against quantum attackers due to the inclusion of the post-quantum chems. Similarly, we should still have security against classical attackers, even if both the QKD and the post-quantum chems fail, perhaps due to flaws in the potentially understudied or assumptions, or maybe flaws in the underlying implementation. But what about robustness in the face of differing compromise models? So imagine a timeline of key exchange protocol executions along this x-axis here. So a key exchange has forward secrecy if an attacker with complete network control manages to compromise the long-term key of that party. Obviously, key exchange protocols that are executed after that point cannot be secure, as the adversary can trivially impersonate one of those parties. What about key exchange executions that happen before that point? If the key exchange protocol manages to retain security before the compromise took place, then we say that the key exchange has perfect forward secrecy. Similarly, post-compromise security is sort of the inverse notion. So the idea is that an adversary, again with complete network control, compromises the full state of a party. Now at that point, it's trivially obvious to see that an adversary can impersonate that party and thus get no security from key exchange executions that happen after that point. But what if we add the restriction that the adversary has to be passive? Well, if the key exchange protocol can lock out or regain security after key exchange executions after that point, then we say that the key exchange protocol has post-compromise security. So, to summarize, we get our quantum safe key indistinguishability via the inclusion of QKD and post-quantum chems. We get breakdown resilience, again, by the inclusion of redundant post-quantum chems, QKDs, as well as this classical key encapsulation mechanisms. Forward secrecy is fairly straightforward to explain. We use single-use chems that are authenticated via some other mechanism in order to achieve forward secrecy. Post-compromise security is going to be explained once we talk about how Muckle itself is constructed, so stay tuned for that. But what about authentication? Let's get into that now. So the initial idea was that we already had a QKD authenticated channel. And so in order to make things simpler on ourselves, which is the goal of every cryptographer, we thought, well, what if we sent the key exchange messages, the key encapsulation messages, in that authenticated channel? Then we wouldn't have to worry about authentication at all. Unfortunately, that approach was problematic. So for one, we wanted breakdown resilience, which is to say that if the security of the QKD is undermined, then the key exchange protocol remains secure. Obviously, if the QKD authenticated channel is compromised and we're sending unauthenticated messages within that channel, that no longer becomes true. In addition, as a kind of orthogonal point, interleaving the key exchange or key encapsulation messages with the basis information was problematic. However, as a result of kind of this thought process, we stumbled upon the following notion, which is, in practice, establishing two pre-shared keys is not significantly more expensive than establishing one. So what if we use the same approach? Only we use the secondary pre-shared key as the key to a message authentication code, which we then use to authenticate the key encapsulation messages or the key exchange messages exchanged between the two parties. Sufficiently large keys give us quantum secure authentication. Awesome. So now that we have that, we can combine all of these observations together, and I can present to you Muckle. So Muckle is a multi-stage, one-round trip key exchange protocol that parties are meant to consecutively execute between each other, and has a fairly straightforward design. So at the beginning, Alice uses the key generation for a key encapsulation mechanism and a post-quantum key encapsulation mechanism to derive pairs of classical and post-quantum public keys, and then uses the pre-shared key established between Alice and Bob, as well as some secret state, which we'll talk about in a minute, to generate a MAC key. And then straightforwardly, Alice generates a MAC tag, which is over the pair of public keys and some header information. And the message that's sent between Alice and Bob is simply the pairs of public keys, the header information, and this MAC tag. Bob, straightforwardly, uses encapsulation algorithms for both the classical key encapsulation mechanism and the post-quantum key encapsulation mechanism to generate a pair of ciphertexts and a pair of output keys. Similarly, Bob uses the pre-shared key as well as the secret state and some labels to distinguish the two to generate a MAC key and then a MAC tag over the header information and the two ciphertexts, so the output of the key encapsulation mechanisms, and then sends across the two ciphertexts, the MAC tag, and the header information. Alice uses the decapsulation algorithms associated with both of these key encapsulation mechanisms to generate a classical key and a post-quantum key. And then finally, in the last step, Alice and Bob derive a secret state, which is used in the inclusion of the following stages, as well as keys that are output via the Muckle key schedule, taking as input the classical key that is associated with the classical key encapsulation mechanism, the post-quantum key that's associated with the post-quantum key encapsulation mechanism, the quantum keying material that is the output of the QKD, the pre-shared key, and the secret state from the previous stage, as well as both messages that are sent by Alice and Bob. So, the hybrid approach manages to achieve breakdown resilience via the classical chems, the post-quantum chems, and the quantum key distribution components. This evolving state using the secret state in the derivation of the MAC keys and then the derivation of the following secret state manages to achieve post-compromise security. The use of our MACs help us to achieve post-quantum authentication. And one of the cool things about this is that the key confirmation messages, which is essentially the MAC tags that are sent in successive stages, provide us with full message transcript of previous stages. And so Muckle is a fairly straightforward key exchange protocol. But we didn't stop there. So we also implemented Muckle in C and did some benchmarking tests. So as our dependencies, Muckle required embed TLS, which is used for HKDF in order to implement our Muckle key schedule, which you can see here on the right. We use HMAC for map computation, both with SHA-256 as the underlying hash function. We use ECTHE using curve 25519 as the underlying classical key encapsulation mechanism. And we also use entropy generation for random seeds. For the post-quantum chem side of things, we use PQCrypto SID, which is used for obviously SIDH key generation and secret computation, which we use in our instantiation of the post-quantum chems using SIDH 503. So in terms of our results for benchmarking, we had a series of Walltime experiments that were performed in two different setups. The first was we had two Amazon Web Service dedicated instances in two different availability zones, but within the same London region. Unfortunately, we don't know the exact distance between the availability zones, but we do have some ping results, which helps us to sort of determine what the distance looks like. We do 100 of these experiments, and each process is pinned to a single CPU. Unfortunately, we were unable to get QKD hardware set up with the AWS instances. We instead emulate the QKD by reading from a static array of random bits on both sides. And these are the results of our Walltime profiles. On the right here is the two different availability zones, but within the same region. This actually more accurately represents what a QKD setup would look like, unfortunately, because the distance between the two communicating parties must be small. And you can see here that networking takes up almost the majority of the Walltime profile. Pretty much everything else is devoted to the SIDH generation and computation. You can see here in black and red that ECTH takes up a not insubstantial amount of the Walltime. Whereas our Walltime profile between two different instantiations in two different regions, which is London and Paris, networking time is now dominating the Walltime profile. For the same region, ping time was 0.745 milliseconds, but the total execution time for a single Muckle round was 12.9 milliseconds. And we also proved Muckle secure. So in order to do so, we introduced HAKE protocols, or a hybrid authenticated key exchange security model. Our security model is an extension of extended kinetic crawl check style AKE security properties. So a little bit of background on what that looks like. So as I said before, Blair and Rogaway introduced a security model for authenticated key exchange in 1993. And security was defined by two properties: authentication, which was agreement on some sort of session identifier. You can think of that as the message transcript, and key indistinguishability, the adversary's ability to distinguish between a real key that was computed during the execution of the key exchange protocol and a random key that was sampled from the same distribution. Now, our adversary has to answer this real or random challenge, has complete control of the network via send queries, but is also able to corrupt and compromise. So corrupt refers to long-term secrets, corrupt the post-quantum keys, corrupt the classical keys, and corrupt the shared symmetric keys established between the two parties. And then compromise is kind of the ephemeral version of that. So corrupt was for long-term keys that were used throughout multiple stages in the key exchange execution, whereas compromise would be revealing ephemeral randomness that was used in only a single stage of the protocol. The adversary can also win by breaking authentication, forcing a client to reach an accept status, but without an honest contributing partner. We define security for HAKE protocols against two types of adversaries. The first is a classical adversary without access to a quantum computer. And the second is a quantum adversary, which obviously has access to a quantum computer. These two different sets of queries two different sets of adversaries relates to two different sets of queries that the adversary is allowed to issue. On a high level, a quantum adversary can issue corrupt and compromise queries for the classical secrets. So think here of maybe RSA secret keys, or maybe ECDHE ephemeral randomness that's used during a single stage without restriction. But a classical adversary, on the other hand, is restricted from freely issuing such queries. So we have some cool benefits and limitations of our model. So one of the coolest things I think about it is that the model is more general than Muckle. So as you saw before in our Muckle construction, jumping back quite a few slides, we don't use any like long-term asymmetric keys as authentication or inclusion in the key derivation. But our model manages to capture the adversary's ability to corrupt those keys. In addition, I think it cleverly captures QKD. We model them as a set of pre-shared ephemeral symmetric keys. So for instance, if we wanted to model an adversary that is able to break the underlying QKD, maybe due to flaws in the hardware, the adversary will issue a compromised symmetric key, and that'll allow them to reveal the quantum keying material that's the output of the QKD. And then finally, one of the things that made it good to actually prove in is that it's a quantum standard model, so there's no need to manage the quantum random hierarchical model. Unfortunately, there's additional restrictions on authentication. This is due to the nature of Muckle itself. This is in a cleanness predicate that we use to restrict the adversary from issuing trivial win queries. Specifically, if there exists an origin session, which is to say a session that has sent the message that one of these sessions receives, we can't issue corrupt queries to either of the two parties until that session has completed, which unfortunately is a bit of an additional restriction. In addition, the adversary only has classical access to these queries, cannot ask for evaluations of like compromise CK or compromise QK, for instance, on superpositions. And then we are able to prove in our HAKE model that Muckle is both quantum and classically HAKE secure based on some assumptions, post-quantum assumptions of the PRF, MAC, and key encapsulation mechanisms. Yeah, that's the wrong direction. So to summarize, in this project, we looked at quantum key distribution, and we looked on how to integrate QKD formally into an AKE protocol and security model. We introduced Muckle, which was a one-round trip, quantum-safe, hybrid AKE protocol with perfect forward secrecy, breakdown resilience, post-compromise security, and other fancy acronyms. We generalized and expand upon previously established AKE security properties for hybrid key exchange protocols. We analyzed and generated proofs for Muckle, and then we described our implementation. And it's available right now with our benchmarking results. So please feel free to enjoy, and please ask us any questions. Thank you very much.